Yeah, we'll be resuming the session. Everyone outside, please come in. Good afternoon. My name is Hong Im. I'm another co-organizer for the event, and I'll make a quick announcement. First thing is, those the invited speaker guests, we are organizing a nice cultural tour at the end of the conference on Wednesday late afternoon. So those must have received an email invitation already. So it should be in your mailbox. So if you can, and I strongly encourage you to participate if you can at all, and you should register online. There's a link on the email that you got. So please make sure to sign up for it. Another one is an important announcement is for those who are visiting here on a kind of daily basis, the visitors in and out. Make sure on your way out at the end of the day, please check out at the gate. If there are two lanes, and you should take the inner lane to see the booth and see the security officer to make sure you check out. Otherwise, there's a alarm. They will be notified, and there's some complications. So please make sure you check out every time. All right, and the afternoon session is starting. Will be chaired by Professor Sarathy, you saw this morning.
Okay, good afternoon, everybody. So I'm the chair of the session, and I'll be introducing the first speaker. His name is Mani Sarathy, and oh, that's me. Okay. So, okay, jokes aside. Okay, hi. That's how I introduce myself. Hello. Okay. So I'm going to be talking about some of the work that's being done here in Saudi Arabia, specifically in Neom, around hydrogen and e-fuel solutions for the second energy transition. I work half my time there for the last 2 years and a bit, and I'm also here a faculty at the university. Now, this is not Neom is a company. The energy water company of Neom and Enowa, who I work for, is a company. So we're trying to build real world solutions that are relevant to Neom. So it's not so much R&D. So it's not going to have graphs of all the details and technical analysis, which of course I appreciate as an academic, but it will be more of a techno-economic perspective of what could be possible if we were to develop a hydrogen economy at scale. And what are the challenges associated with that we are encountering. So hydrogen today is quite widely produced. Of course, it's coming mainly from petroleum or fossil-derived resources, natural gas, coal, and a lot of the hydrogen, about a quarter of it is associated with byproduct hydrogen formed with syngas in form of CO and hydrogen. And then on the left-hand side, your right-hand side, you can see also where this hydrogen is being used. The demand is mainly ammonia, which is a fertilizer, and refineries, which use hydrogen for hydrotreating and various petroleum upgrading processes. And we see some smaller amounts of hydrogen being used in other areas like the production of methanol, a little bit for reducing iron, from iron ore to iron, and also other heating applications, mainly again in industrial processes. In the future though, this about ballpark 100 million tons of hydrogen used annually a year will expand significantly. And today, again, 90 to 100 million tons, depending if you count the associated hydrogen with syngas or not, is expected to increase significantly over the next 3 decades. And of course, that's largely due to the need for various economies globally to reach their net zero carbon emissions. And in the next 10 years, maybe about 150 million tons, but by 2050, forecasts are saying upwards of 600 million tons of hydrogen. Now, that's a huge amount of hydrogen. And this is then the demand sectors where these will be used. Most of it is going to go to mobility, road, aviation, maritime, and other forms of transport, because they are the hardest to decarbonize. And then ammonia industry will use slightly more. Again, this is existing ammonia for fertilizer applications. It does not include new applications of ammonia, such as for power. And then things like industrial applications. So In Neom, we're mainly interested in how do we capture the market together with the partner companies for the largest demand sectors. And so it's going to be mobility, steel, and some industrial applications, not including the heat. Heat applications are not so much relevant in Saudi Arabia. So you know the different colors of hydrogen: gray, brown, black, coming from fossil fuels; blue hydrogen, hydrocarbons with CO2 capture; and green hydrogen, or hydrogen from renewables, is what Neom aims to be a leader in its production. And it's important to keep in mind that just because you make hydrogen from water electrolysis, it doesn't necessarily make it low carbon footprint. On the chart here on your left, you see the carbon footprint. We saw it earlier as well for hydrogen coming from different resources. So SMR, you're producing about 9 kilograms of CO2 per kilogram of hydrogen. Autothermal, you can get a bit less. If you do carbon capture, you can get about 90 to 95% of that CO2 captured. So you can come down to about 2 kilograms of CO2 per kilogram of hydrogen. But if you use electrolysis of grid power in most countries, which is over 50% based on fossil fuels, then the carbon footprint it can be double that of just making it from methane. So it really needs to come from renewables, or a large fraction from renewables, to have a low carbon footprint. And the chart on your right shows, again, for different countries, if you just use the grid to electrolyze water, from many countries like Netherlands, Czechoslovakia, Ireland, Germany, in addition, in UK, all of these countries, the CO2 footprint of that per megawatt hour of hydrogen produced is larger than that of just gray hydrogen. So only countries where have large amounts of renewables or nuclear power is where you can do water electrolysis with a low carbon footprint. So in Neom, the goal is to do water electrolysis with renewable energy, but it is challenging. And I work in technology innovation side of the Enowa business for hydrogen, and try to address what are the various challenges that need to be overcome for this large-scale hydrogen economy to be a reality. And today I'll just highlight some of them. Technical challenges related to feedstock quality. Production of e-fuels is not easy. There's also economic challenges related to capital costs and operating costs. And I'll put this all in the context today around transportation fuels. So if you were to use hydrogen or ammonia, methanol, or other types of e-fuels. So first, for those of you who've never heard about Neom, just a couple of minutes overview. It's a region, an entire region in the northwest of Saudi Arabia. You see it's bordered by Jordan. Israel is up here. This is the Egyptian Sinai Peninsula, and this is the Gulf of Aqaba and the Red Sea. This whole area is about the size of a small country, Belgium. And the goal is to have something like 9 million people living there in the next 20 years. But right now, there's about 3,000 of us living in trailer parks in the desert. It was selected because it's a good location, one for tourism, but also for energy. So a lot of the Europe, Asian trade routes are within a 4-hour flight away. But then you also have the Red Sea, which is rather pristine in that region. And then the temperatures are fairly cooler compared to here in Jeddah or other parts of Saudi Arabia. Key to note is a high solar intensity and high wind speeds. Actually, just last week, they had the Neom Beach Games. It was a World Cup of kite surfing. So it's a very good place for kite surfing if you're interested because of the high wind speed. Also good for windmills then. And Neom has to have its own economies. Water production, energy production, mobility, as well as many things like sports, food, tourism, excuse me, and entertainment and digital technologies. And my goal is to work in the energy area and specifically on hydrogen. So the availability of wind and solar resources in that region makes it amenable then to install renewable energy. And of course, with large excess of renewable energy, hydrogen can be a viable technology for deployment. So Neom's energy strategy is quite ambitious. They want to be 100% renewable energy. Now, 80% is actually pretty easy and doable. 90% gets hard. 100% is very, very difficult, because you can imagine there's nothing to underwrite whenever the renewable energy is not available. Not only the availability of energy, but how you manage 100% renewable energy system is very complicated, because consumers are always having fluctuating demands down to the second basis, and renewable energy is not a constant supply. And then you also need large amounts of backup and excess capacity. Now, we want to use this renewable energy then to drive clean energies intensive industry as well. I'll skip this one. So Enowa is the energy water company of Neom. It's called Enowa because it's energy, EN, and water, WA, and the O is a circle. So it's nice marketing, a circle of possibilities. Okay, so there's a short video. I'll show the video now for Enowa. Can you get the sound?
Green hydrogen, nature's secret. And as a
Sorry, I don't know what happened there.
green hydrogen, nature's secret. And as a partner of nature, Enowa is bringing people, industry, and technology together to make the world's first at-scale green hydrogen production facility. In harmony with nature, Enowa will use solar and wind power to produce green hydrogen, which can be used for energy applications around the world, impacting people without impacting the planet. It's possible to change the world and protect it. Enowa, a circle of possibilities.
Okay, so with good marketing budget, anything sounds great, yeah. But there's of course not as easy as making the video. So we got to do real innovation and technology, and of course scale up to make sure that these things are potentially realizable in the future. So in Enowa's innovation roadmap, there's 3 phases. We have, of course, large-scale projects like the big green hydrogen project with Air Products and Aqua Power, which I'll talk about briefly. But also we're doing the Hydrogen Innovation Development Center for pilot scale technologies, and then an Applied Research Institute, which is very similar to a research center for hydrogen that you would find in a university. Can you give me some water? So I'll talk about some of those techno-economic challenges around the hydrogen production, ammonia, and also methanol. So the low cost first, the production of hydrogen. There's going to be several innovations that are required in terms of reaching the scale that's needed to get the cost very low. And I'll also try to give some rationale why we select certain technologies for large-scale production today. So this is a nice chart just showing the TRL for different hydrogen-related technologies. Thanks. So if you see the technologies that are very mature, like alkaline-based electrolyzers and PEM electrolyzers, things like solid oxide electrolysis are relatively lower TRL, but are rapidly increasing in their technical viability. Things that us university people like photocatalytic water splitting, photoelectrochemical water splitting, using bacteria to make hydrogen. These are very low TRLs, and it's unlikely that they're going to make a huge contribution to the hydrogen economy in the next 20 years. So really, when we talk about scale and implementing the economy, we're trying to focus on things that are TRL 7+. So water electrolysis can be done by various means. Alkaline-based systems are and PEM-based systems are relatively low temperature. They might operate around 90 to 100 degrees Celsius. And then you have a solid oxide electrolysis, which operates at much higher temperatures. The benefit of the alkaline and PEM systems are lower temperatures, so you get better material compatibility, You don't need excess heat to drive the process. And then with the PEMs, you can get higher current density. Now, the benefit of a SOEC, though, is much higher efficiency. So we asked the question first, which technology should we go for? Should we go for efficiency, or do you go for scale? Today, this is showing the ballpark efficiency of different electrolysis technologies. Alkaline, about 70%, let's say 80% for PEM, and upwards of 90% for SOEC. But if I want to go to the market today and buy a good size electrolyzer, the SOEC is less than 1 megawatt. PEMs, you might get in the 1 to 3 megawatt. And alkaline, you can buy 20 megawatt systems today. So today, for scale applications, it is alkaline-based systems. In the next 10 years, the goal is to try to adopt some PEM. SOEC, there's some companies like Sunfire and Halder Topsoe, which are trying to scale them up. Maybe get the market in 2035 onwards. Now, hydrogen has a heating value of about 33.6 kilowatt hours per kilogram, or 11 meter cubed per kilogram, and m cubed per kilogram. And you see here why SOEC is just much more efficient is because once you cross 100 degrees Celsius, the Gibbs free energy related to water electrolysis becomes lower because now you're dealing with steam instead of liquid. So if you're up here at 700 degrees Celsius, the delta G is lower, so you get a better efficiency. But it's not only about what can you do to get efficiency. In addition to making the hydrogen, you got to compress it. Compression of hydrogen using typical industry technology is about 85 to 95% efficiency to get to 350 bar. So we're pretty good at compressing hydrogen today, and we're not losing so much in that step. Some people ask, we're here in Saudi Arabia, there's no fresh water anywhere. Does it make sense to take seawater and make hydrogen? And you might ask yourself the same question. We're going to desalinate all this water and make many, many tons of hydrogen. Well, it's really not that much of an issue. 1 kilogram of hydrogen only needs 9 kilograms of water. So again, so let's say we need 1,000 tons of hydrogen, you need 9,000 tons of water. That's 9,000 meter cubed. That's a very small desalination plant. Here at KAUST, for a city of 7,000 people, our desal plant does 20,000 meter cubed a day. So already 2 times the size of a relatively large hydrogen plant. So the amount of water that's required and the efficiency of desalination is also very effective. And people then always say, you need to desalinate all that water, it's energy intensive. Well, again, to split hydrogen is 50 kilowatt hours per kilogram. To desalinate water is a factor of 1,000 times less, 0.003 kilowatt hours per kilogram. So the energy demand of desalinating water is negligible on the whole balance of plant. It's the requirement for splitting the water molecule, which is the most energy intensive. So where are the challenges with electrolyzers? It's bubble formation. So you're taking a liquid, you're putting an electrode, and bubbles of oxygen and hydrogen are forming at the electrodes. And those bubbles are leading to reduced surface area for chemical reaction. So what the electrolyzer manufacturers are trying to do are coat the surface so you get better evolution of the bubbles so they don't stick to the surface, or modifying the operation of the electrolyzer so you minimize bubble formation. In addition, you got to operate these electrolyzers under variable renewable energy. So there's a lot of interest to find out how to cycle the electrolyzer most efficiently under variable energy conditions. In addition, we got to scale up the manufacturing of these electrolyzers. You need a lot of materials like catalysts, separators, membranes, bipolar plates. So the goal is today we have about $850 per kilowatt. Excuse me. But in the next 10 years, the goal is to drive that cost down by about 50%. So it'll come down to about $300 to $400 per kilowatt. Now, once you have the hydrogen, you want to do stuff like make ammonia. Making ammonia is a pretty straightforward process by Haber-Bosch. But what do you do with that ammonia after you make it? Well, you got to transport it. And in countries like Europe and North America and Japan, they might want to reconvert the ammonia back to hydrogen at some point in utilization. So the scaling, the large scale production of ammonia, industry leaders like Air Products, Aqua Power are joining forces with Neom to make this a realizable project. And they've adopted scalable technologies from companies like ThyssenKrupp, Halder Topsoe, to make it possible to produce ammonia at a very large scale. 650 tons of hydrogen going to make 1.2 million tons of ammonia per year. Now, once that ammonia is made, it will need to be transported. So this facility will produce the ammonia in Neom, 1.2 gigawatts of wind, 2.2 gigawatts of solar, 2.2 gigawatts of electrolyzer capacity, and then an ammonia plant with some intermediate storage will make the ammonia, which is then put on a ship and sent around the world for markets that want to decarbonize. Now, the challenge here is, okay, it looks fine here. So if you want to sell this ammonia, or say low carbon hydrogen to Germany, you have to meet their benchmark carbon intensity. So today, EU benchmark is 94 grams CO2 per megajoule. That's gasoline used in an ICE. If you want to meet the RED II standards for renewable fuels from non-biological origin, RF, NBO, you got to get 70% carbon intensity savings. So about 30, let's say, grams CO2 per megajoule. So if we look over the entire process, where is the CO2 has to be saved? Well, first in the production, they'll make it at a pretty low CO2 footprint, about 40 grams of CO2 per kilogram of ammonia. Then you need to transport that ammonia by sea. So you emit about 65 grams of CO2 per kilogram of ammonia by ship transport. It's quite efficient. Then you got to take it from a terminal, say in the port of Rotterdam, to a road transport to a station. You might emit about 90 grams CO2 per kilogram of ammonia being moved. And then finally, you need to crack that ammonia back to hydrogen for a filling station. And that actually turns out to be a challenge. So the NH3 cracking, of course, it depends how you do it. If you use natural gas for the heat of that process, you'll emit about 161 grams of CO2 per kilogram of ammonia. So we need to, if you want to decarbonize this process, use something other than natural gas. And also then the compression, if you want to get to, say, 350 or 700 bar, if you use electricity for that, the compression, say the German grid, is already carbon intensive. So you actually emit 259 grams of CO2 just by compressing to 700 bar. So the total then comes pretty close, 33 grams of CO2 per megajoule. So most of the challenge is going to be in the sectors where these fuels are going to be required, is to decarbonize those economies, because it's not just about delivering them a low carbon feedstock. They need to make sure their electricity grids, their own industrial processes then used for reconversion are clean. And then if we want to use ammonia for shipping applications, it looks to be a viable solution. This is a chart from the IEA, Future of Hydrogen, total cost of ownership. And we see here that today ammonia is very expensive in IC engines compared to fuel oil. But in the future, the expectation is that IC engines will be technically viable solutions for ammonia use, and the TCO could be quite comparable to what fuel oil is today. Now, what about carbon-based e-fuels like methanol and others? So carbon-based fuels are good for road transport because they have higher energy density than lithium-ion batteries or compressed gases. We see here methanol, 4 kilowatt hours per liter, still about a factor of 2 lower than petroleum. So the total cost of ownership for various low carbon solutions is shown here. These are for light duty vehicles. And we see here that in the short term, of course, ICEs with hybrid electric engines are viable. Battery electric vehicle technologies are more expensive. But long term, we can expect that fuel cell electric vehicles, battery electric vehicles are competitive. And the ICEs operating on e-fuels the engine solution and the infrastructure costs are low, as well as the operations and maintenance, but the fuel production cost, and mainly coming from air capture of CO2 and synthetic fuel production, is still large. So, and these are open bars because there are major uncertainties. So really, if we want to make this technology viable, it's going to come down to the low cost production and the sourcing of the CO2 in a cost-effective way. So that's what we're trying to do at the Hydrogen Innovation Development Center. We're trying to build first just pilot scale facilities for e-fuel production to show that these are viable technologies and that they could be scaled up. And the first thing to do is to work with industry partners. So we're working with Saudi Aramco on a methanol plant. We're also working with Aqua Power and Air Products for the hydrogen production. And this is the overall facility layout. There's phase one, which is owned by the joint venture. So there's an electrolyzer, which is producing about 9 tons a day of hydrogen, and that's stored and then sent to filling stations. And then the e-fuel value chain is together with Aramco, where CO2 is captured and stored on site, and then it's used to react with the hydrogen. About 2.5 tons of the 9 tons will go to make methanol, and then the methanol will be converted to gasoline in an MTG process. So the methanol process is shown here. You take power, you electrolyze water. You got to compress your feed gas to about 50 to 60 bar for the reactor to operate. So CO2 and hydrogen at 50 bar. And then the methanol synthesis reaction happens in a copper zinc oxide catalyst. A single pass conversion is about 30%. So you need a large amount of recycle of the gases coming out, which are then fed back into the reactor. And then the liquid, of course, is separated out and then sent to distillation. So after large amounts of recycle streams are incorporated, you can get almost nearly 100% conversion of the feed CO2 or the feed carbon into methanol. And of course, you also get water as a byproduct. The major capital costs here, though, are these compressors. So compressing CO2 and hydrogen to 50 bar, and then the large amount of recycle also requires recompression of the stream. So those compressors are about 15% of the overall capex on the plant. In addition, the methanol process is shown here. So energetically, it looks nice, yeah, because you take CO2 and hydrogen, you make carbon monoxide and water, mildly endothermic. Then the next steps are exothermic. But we keep in mind that we still need to split the hydrogen from water in the first place. So we take CO2 and water. In the end, we get methanol and water. And overall, most of the energy went into actually producing the hydrogen for the process. And then if we look at the overall cost of this process, it will depend on the capital cost. But if you amortize this over a large plant over 20 years, capital costs are manageable. It's mainly feedstock costs for hydrogen and CO2 that affect your bottom line. So here we have the price of CO2 per ton and the effect of that on the methanol price. And the different colors are just different estimates for hydrogen price. So we can expect in the near term, maybe $2 to $3. Hopefully in the long term, we can come down to $1 per kilogram of hydrogen. Now, if we want to reach an acceptable price of methanol, say $350 per ton, we need hydrogen to be around $1 per ton, $1 per kilogram, and we need CO2 at about $80 per ton of CO2. $80 per ton of CO2, if you go for air capture, very unlikely in the near term. Maybe a point source capture could be realizable. If we talk about air capture, it's upwards of $400 or $500 a ton today. And I don't see a roadmap in the next 10 years to get that below 100. So, I mean, bottom line here is that we can get hydrogen costs pretty low, but still the CO2 capture costs, if we are so dogmatic that we need to stick to air capture for making e-fuels, are going to be a challenge. And this is the debate that's happening now. What is acceptable CO2 for e-fuels? If it's from a point source like a cement plant or or a power plant, you can easily get CO2 at a reasonable price, $70 to $100 per ton after transportation. But if we need to stick to air capture, it's going to be very difficult to make this a viable technology in the next decade or two. So yeah, I thought these just highlight some of the challenges that need to be overcome around the e-fuels, and including ammonia, hydrogen, and carbon-based e-fuels, and then highlight those technical challenges, but also economic challenges. But again, I think these are all challenges. All of them can be overcome. None of them are beyond our abilities. So happy to have your questions. Thank you. Yes, Gaetano.
So for the European market, is it on? Yeah, it's on. So for the European market, is it more convenient, I mean, from an economical point of view, is it better to ship ammonia or a pipeline for hydrogen directly, since the cost of cracking and?
Yeah, well, there's now discussion, I think, in the national hydrogen strategy, and then companies like Neom, Aramco discussing the potential for a pipeline. Somebody's got to pay for it. It's very expensive. I think they're saying about it's about twice the cost of a CO2 pipeline. So it's about $2.5 to $3 million per kilometer. So you got to go 5,000 kilometers. So it's a several tens of $billion investment. Now, if the volumes are large, it does make sense, yeah, to go pipeline. But the volumes have to be very large. There's also some geopolitical issues, right? If you have to cross through Egypt and North Africa, and then I think the shortest route now they're saying is to the northern part of Egypt, then Algeria, and then over to Italy or Greece, one or two. But there's an MOU between the Saudi government and the Greek prime minister around hydrogen pipeline connection under the Mediterranean, and also the Italian company. Not ENI, it's the, say again? I forget the name, starts with S. Snam, yeah, Snam, yes, exactly. Thank you. So these discussions are happening, but again, I think it's going to be like some countries, few countries along this route, putting down the big investment. And then, of course, an offtake agreement from the Europeans to buy the hydrogen that's coming. More questions?
Yeah, I just got a question. Why do we need to transport hydrogen again? I mean, it's not like oil only available in certain places. You can just make it in place and just use it.
Yeah, it's a good question. So I should have mentioned clearly. So countries like Northern Europe, Germany, Netherlands, Scandinavian countries, also Poland and all, they don't have enough renewable energy available to fully decarbonize their entire economy. So they might only have about 45% of the renewable energy available. So they need to import that energy from somewhere else. Now, one possibility is you build supergrid from North Africa. They tried this, I believe, the project Desert Tech or something. In Morocco, they tried to put large-scale solar farms and then built underground cables going to Europe. There was a lot of issues with that project. I don't think it ended up being successful. And the other option is hydrogen. Similarly, Japan is quite void of available renewable energy because of land limitation. So they want to import the energy. But other countries like North America, Canada, United States, they're unlikely to need to import. I mean, they will have enough land and enough resources locally to produce hydrogen, to decarbonize things like transport and industry that need it.
Thank you.
Okay, thank you.
Thank you.
Yeah.